Okay, so I am going to show y'all a document from a previous year. Those are the solutions. That's not what I want. Okay, so this is a document that I made in 2019 for the test review at this time, and these were problems from old tests. And so it's so you can get an idea. I went through and I found all these kinds of problems from old tests. So simplifying Boolean functions. Y'all have done don't cares. And so don't cares, prime implicants, listing those, listing essential prime implicants, converting to binary, converting to hexadecimal into decimal, writing sign and magnitude, one's complement and two's complement, and then also adding and seeing if overflow occurs, and then a truth table for a circuit and showing values, and then drawing a circuit based on the Verilog, and then this one about half adders, which was that was the one. I have one kind of like that, as kind of like a different kind. It's like most of them were kind of similar. This one's kind of different. And so what I made for y'all is a problems that are similar to all of those, and that's what we're going to work on. So where did I put it? Right here. Okay. So I'm going to start not in order since y'all asked first about the adders. We're going to do that and we'll talk about adders because a lot of times there are questions on it. And I want y'all to take a look at this one. And before I start it, let's just talk a little bit about adders and half adders and remind ourselves of what they are. So what's the difference between an adder and a half adder?
Half adder takes two inputs. Half adder and full adder?
Yeah, that's what I meant. Half adder and full adder. And what's the difference?
Half adder takes two, consolidate summing carry. A full adder takes in three, consolidate summing carry.
Okay, so that's the difference between the two. So a full adder, you can add the carry in bit. So like if I were to add these numbers, if I were to try to add these numbers together and I take 1 and I get 0 and I carry the 1, if I'm trying to design this circuit, a half adder doesn't do a whole lot of good because I can't take these three inputs right here. So a full adder would be better. But this is saying to use a half adder just to increment a 4-bit unsigned binary number, not to add two numbers together, but to increment a number. So I want y'all to think about this and talk about it with each other and see what you can come up with, and then we're going to go over it together. But I want y'all to have a chance to think about it yourself first before we go over it. I want to talk a little bit more about adders, so I lied. What's the difference, because you had asked about them, what's the difference between a ripple carry adder and a look ahead. What's it called? A look ahead? Just a look ahead adder? I should know because I actually did the lecture on this last semester.
It is a carry look ahead adder.
Carry look ahead adder.
You're a sub?
Only when he can't find it. When he's gone through everybody else. I'm the bottom of the barrel and they'll ask me. Yeah. So what's the difference between these?
So that a ripple carry is multiple full adders put together. Carry look ahead adder is a quicker version that uses more gates.
Yeah. So a ripple carry adder, this one adds like we add. You start at the left, so 1 0 1 1 0 1 1 0. 1 0 1, no carry, so our carry is 0. 0 plus 1 plus 1 is 0, carry the 1. 1 plus 0 plus 1 is 0, carry the 1. 1 plus 1 plus 0 is 0, and then our carry out is 1. And so that is a ripple carry adder. It's called a ripple carry adder because it ripples. It's like you do this one and then you go to the next one and then you go to the next one. And it's like the adder here, the adder to add these last ones can't do its job until all the ones before it have worked. So this one you would need 4 full adders. I guess you could use a half adder for the first one, but you wouldn't want to have that. You'd still want to have a carry in because you never know what else you might have had before this problem. And so you have that, and it's fairly simple. A carry look ahead adder, on the other hand, if we take a look at it, oh, I don't have it on this computer. Okay, so this is a ripple carry adder. Makes sense. You do your 1-bit full adder, then your 1-bit full adder, and your 1-bit full adder, and it just goes through like that. So that's a ripple carry adder. A carry look ahead adder looks like this, and that is just part of it. So here we have one. So this one is one that would be for 3 bits. And so if you look at that, it's quite a bit more complicated as to what's going on. But what's happening with it, the way it's designed, it's pretty ingenious. It can all happen at once. And so you don't have to, it's kind of amazing because you think, well, how does it work? And if you spend enough time with it, you can see how it works. But the amount of time that it takes to compute the sum is, if you just look at your inputs here, so here are your inputs, and you just look at how many gates they have to go through to get to the output, it's only 2. At the level, it's 2 all the way across. No matter which one you're looking at, it's only 2. So it goes a lot quicker. But look at not only how many gates you have, but how many inputs to those gates you have. And so that gets a lot more expensive. So that's the difference between those. So you had asked about those. I haven't seen a question on a test about that. What I've seen is the one like I'm showing you right now, but it can't hurt to understand it.
So
Okay.
real quick.
Yeah.
With the carry look ahead adder, is that just regular OR gates instead of the exclusive ORs?
In this diagram it is. I can't remember the one that y'all have in your book.
Okay, because I know with full adders you use OR gates. I was just curious if with carryover, if they also use OR gates.
This is, yeah, that looks correct right here. The Boolean function for each stage in a carry look ahead adder, that looks correct. And so so this is showing you what your I will get it for y'all while y'all are working on it. I'll get you what it is. I think it is just an OR gate.
Okay.
Yeah. So y'all work on this and see what you can come up with, and then I will have the answer to your question. Okay, so the carry look ahead adder, the implementation that you have in your textbook does include an exclusive OR. Let me see if I can get it for you. So let's see. So if I do this, new, this, and then share this. Oh, I don't have sharing turned on this. Okay.
Turn on the recording.
Well, yeah, thank you. I did actually remember to turn on the recording. I'll share it to my email, and then I can get it for you.
Maybe you have to. By doing this, we're only gonna have 3 used. So maybe you do the same thing, but you also, instead of going 3 of these adders.
Okay, so this is the implementation for the first 2 stages of the carry look ahead adder from your textbook, and it does have an exclusive OR in it. You don't have to have this memorized like how it works, but so you had asked if it had an exclusive OR, and it does have an XOR in it.
Okay.
So it does. All right. So are y'all ready to look at the solution? All right. Or a solution. Okay, it sounded like y'all were on the right track for sure. Just listening to what y'all were doing. Okay, so basically, what are you doing when you increment a number? So if I have, let's just talk about decimal. And so if I have the number 576 and I want to increment that, what am I doing? You're just adding 1. So you're just adding 1. And that's the same thing that we're going to be doing with our binary number. And so we have, what did it say? It was 4 bits, right?
Yes.
And so the way I like to do any kind of coding is think of examples. And so if I wanted to increment this number right here, I would add 1 to it. So let's see how that works. I would add 1 to my first one, and then I will have a carry, and I'll add that carry to the second bit. And so that'll be my input. So even though a half adder doesn't take a carry, there's no reason why one of the 2 bits that it takes couldn't be a carry from the previous one. So it'll be the carry from the previous one plus that 1 be 0, and a carry, and I'll carry, and so then that'll be 1, and my carry would be 0, and I'd get 1. So it seems that what I want to do is I'll have my 4 half adders, and let's call them half adders. And each one is going to take 2 inputs. And my number is B3, B2, B1, B0. And I will take my least significant bit, which is B0, and 1, and I'll add those together. And from those, I will get my sum, and I'll call that S0, and I'll get a carry, and I'll make that carry in one of the inputs for my second half adder, and the other one is going to be B1. So essentially what I did is I took these 2 and I added them to, I took this and I added it to 1. And then I'm outputting the sum, which is right here. and I'm taking the carry, and I'm putting the carry in with the second bit of this one. And then I will output the sum here, and the carry here will go there, and I will put in my other input will be B2, and then sum 2, and I'll have the carry, and B3 will go here, and my output will be S3. I also have this carry, but I'm not doing anything with it. The only thing that I want to check now is, will it happen that 1, 1, 1, 1, 1, 1, 1, will I get 0, 0, 0 if I started with 1, 1, 1? And let me just check that. 1, 1, 1, 1, plus 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, and then I have my extra carry out. So yeah, so that works. So this is all it is, right there. That is your circuit.
Just ignores the final.
Yeah, we're just not doing anything with it.
Now, it said something about labeling outputs as D3, D2, D1, D0. That's essentially what S is.
That's S, yeah, yeah.
And also, on the test, whenever asking for like half-adder circuits, that is an acceptable solution.
If it says given a half adder, then yeah, you do not have to draw. I have never seen him ask you to draw the circuit for an adder. He might give you one and then ask you some questions about it, but I've never seen that. Okay, so